All right, welcome back. So now that we have our stress tensor defined, let's go back to this original cylinder and look at how the stresses would behave at points A, B, and C as I apply some forces on this object. So let's start by pulling the end of the cylinder. So if I pull the end of the cylinder, shown here, and I were to look at A, B, and C, of course I could do a section right through where I'm interested, this A, B, and C, and I would see something that looks like this. The stress profile on here would be the same regardless of whether I'm at A, B, or C. And this is our sigma. We're in tension. The equation for a tensile stress, or a pulling on the end of the cylinder, is one of the first ones we did in here, which was the stress is equal to P over A. And now this is the same at A, B, or C. Now if we have to talk about the subscript, or what direction this stress is applying, we'd have to say, well, what face is this? Or I guess more technically, what face is that? The perpendicular axis to that face from the very beginning we said was the x-axis, and the stress is pointed in the x direction, so we end up with sigma x. So for A, B, and C, we have the same looking stress tensor, and the only value is in our xx placement, so that's P over A, 0, 0, 0, 0, 0, 0, 0, 0. It's probably the easiest type of scenario. But what if instead I were to pull up on the end? Now things get a little more complicated, because what I would have is I would have both an axial force and a shear force. So how do I know that? If I'm pulling up on the end, I could think about what's going on at point A. Is point A in tension or compression, or neither? And in this case, hopefully you can see it. I need my foam example. It would be in compression. And what about C? Well, C would be in tension, and B is right on the neutral axis, so it is equal to 0. Now, how do I know this? Because we have done I could find the internal moment at that cross section. I know there's a moment. It'd be that force times however far away it is from the cross section. And then what we have done already in this class is we've drawn a profile of our stress. And in this case, we'd have something from that moment that looks like that, right? And it linearly changes. This is not exactly drawn to scale, it looks like. Let me make this just a little bit smaller. There we go. So point C is supposed to be right along this bottom. Point A is at the top, and B is right at the midpoint. That's our neutral axis, right? And we had an equation for that. We said that our sigma is equal to minus my over I. Now, as far as our subscript, this is still on this x face, meaning the x, if I were to draw that in there, the x-axis is still perpendicular to that face, and it's also, what direction is this pointing? Well, this is pointing in the x direction. Now, the other thing I have going on here is I have a shearing force. So I could also look at my shear profile, and the shear profile looks a little something like this, where it's parabolic, maximum at the neutral axis and 0 at the top and bottom. And this is our tau is equal to VQ over IT. Hopefully you didn't hate that VQ over IT equation, because it rearing its ugly head again, right? So with tau, now I have to look at what face and direction. Well, it's still on the x face, and then these arrows are pointing vertically, which is in our y direction from our original coordinate axis, where we said y was up and x was coming out to the right. So I have both going on simultaneously. Now I have to just look at each point. You know, where is point A and B and C, and where is point A, B, and C when it comes to these shear stresses and these with these bending stresses. So I would have three different stress tensors. For sigma A, I start off with this xx direction, my minus my over I. Now, instead of concentrating on the sign, what I like to do to make it a little simpler is just say, is it in compression or tension? If it's compression, we have a negative sign. If it's in tension, we have a positive sign. Well, in this case, point A is in compression if I pull up on the end. So I would have a negative my over I for that sigma xx column. The other one that I have, that's the only thing I have because I don't have any shearing force at point A. So I have 0, 0, 0, 0, 0, 0, 0, 0. And that's what the stress tensor looks like for point A. What about point B? Well, if I look at B, now I have 0 bending stress because it's right on the neutral axis. So I don't have an my over I. But I do have a shear stress. I have my maximum, my VQ over IT at point B. And that is in the XY position. So I end up with 0. And then I have my VQ over IT right there. And what I do for signs on my shears is I say if it's pointing up, I just call it, and if it's pointing the positive direction, as far as my axes, I just call it positive. Signs don't really matter. The material doesn't matter as much as long as you're consistent. And I have another 0 here. Now remember, if this is tau xy, I know that's the same thing as tau yx. Those two have to be equal to each other. So that's going to be in this cell right there, VQ over IT, 0, 0, 0, 0, 0. And then I have my sigma c. It looks almost identical to sigma A. The only difference is that I am in tension on the bottom instead of compression. So that's what my stress would look like, stress tensor at point C. Now the third thing that I can do to this is I can apply a torsion or twisting force on the end. So if I were to twist the end, then we're going to be looking at our torsion equation. And we said we have a shearing stress due to that torsion. It's equal to Tc over J was our equation. The question is, what does it look like in what direction? So in this case, I have to pick a side that I'm going to look at for a cross section. So let's go ahead and say I'm looking this way at the cross section. And you'll find drawing these cross sections will make your life immensely easier when it comes to solving these problems. So if I were to be looking from this side, I would see that A is at the top, B is on my left, and C is on the bottom, and the direction of the torque is going this way. And axis wise, I would see that I have Y going up and I have Z. So what would the stress look like? Well, we talked about torsion, and we said what happens is the stress actually pinwheels around. So I would have a tau going this way, and that way for each one of those points, A, B, and C. Right? So if I look at that point A and I say, what is my subscript on that? Well, it's still on the x face. The x face is what we're looking into because x is coming out at us. And I say, what direction is it pointing? It's pointing in the positive z direction. What about point B? Well, it's on the x face, and it's pointed in the y direction, but it's pointed in the negative y direction. So I'm just going to put a little negative right there to remind me of that. What about point C? That's also negative, but it's in the x face in the negative z direction. So with that in mind, I can develop those stress tensors to look something like this. So what I see is, just like I have the xz over here, I have to have a zx, so I have my symmetry for point A, and it's just a matter of putting them in, keeping my signs and everything else for my 3 points, A, B, and C. But here's the cool part for combined loading is we can add, due to superposition, we can add all of these stresses together. So that would be the final piece of it, is adding all three together. And if I add all three together, all I need to do is go through and say for point A, well, at point A, I don't have anything from the twisting. From point A, I do have something due to the bending. And at point A, I also have something due to this axial force. So I'm going to take that P over A, which is in tension due to the pulling, and I'm going to subtract my my over I, because that's in compression due to the bending. So adding those together, I end up with a total stress tensor for point A that looks like this. I have P over A in the positive direction, minus my over I. All that is in my sigma xx. I've never had anything in my tau xy. And then I say, is there anything in this last column? Yeah, I can see there's, for point A, there's this TC over J. The other two didn't have anything. So I would have a TC over J for my third column. And then I have a 0, 0, and 0. Very awkward to have that big long thing on there. And then I have that TC over J down there in my, this would be my sigma ZX column, right? For B, same idea, but I don't have anything in my XX direction except for a P over A. So down here, all I have is P over A. However, when it comes to my second position over here, I have a TC over J due to that torsion, and then a negative TC over J, and then I also have a VQ over IT. Now notice one is positive, one's negative, meaning they're going in these opposite directions. So I have to keep that straight. For my second little bit here, I have VQ over IT minus TC over J. Then I have 0. And then I need the reciprocal of that down here. So I have VQ over IT minus TC over J. 0, 0, and then 0, 0, 0. It's kind of messy trying to keep all this straight. Hopefully you're seeing this okay, and I don't need to put in these extra little bits, but maybe if your notes, if it's helpful, do it. And last but not least, our stress tensor for point C looks a lot like A. The only difference is I have a change in signs on this my over I, so I have to add those together. So from my pulling, I have P over A, and then I'm adding my bending, my over I, 0. I have my torsion minus TC over J, 0, 0, 0, minus TC over J, 0, 0. So that's what it looks like when I break it all apart and then add it all back together. And so the next video will have an actual example. Hopefully you can follow along with that. Let me know if you have any questions or comments. Thanks.